Good morning, everyone. In our last class, not in last class, in last two classes, actually, we are covering the semantic analysis portion. we have come across, we have came across about the different attributes in the semantics analysis segment. One is synthesized attribute, another was inherited attribute. Synthesized attribute are those attributes. I hope you can remember in the term SC. When means the attributes, the values are coming from the child. C stands for child and inherited IPS I said. So if the values are coming from parents or siblings, then those attributes will be categorized as inherited attribute, right? So today we will be moving to the translation scheme and L attributed definition, and I hope this is the last class on semantics analysis. In the next, we will be moving to the code optimization and three address code generation segment. Okay. Okay. I hope you can see the screen that I have displayed here. Now, let me connect my digipad first. It is connected. Now, I hope you can remember, just I am scrolling up because these portions are already being covered. And last class also I said that what type of questions may come. But I hope you can remember these two part that this entire semantics analysis was categorized into two segments. One is syntax directed definition, another was translation scheme, right? So in our last two classes, we covered these two part as attributed definition because here we seen the synthesized attribute segment and also the inherited, correct? Now today we will be looking at the L attributed definition as well as translation scheme. Correct? First, you need to remember that this L attributed definition, L stands for left actually. Left attributed definition comes under the syntax directed definition segment. And also the translation scheme will be moving. Now, for both the schemes, whether it is a syntax directed definition or translation scheme, the objective remains same. That we will be writing the production rule here, and the right side or anywhere the semantical rules would be there, because our main purpose of this semantical analysis is to evaluate the value of the entire tree, to change the abstract syntax tree into a complete syntax tree, correct? Okay. Now, let us move to the L attributed definition first, then we will be moving to the syntax directed definition. Okay. You can see that here a diagram I have here already some notes I have provided that L attributed definition, what is the definition of L attribute. Just you can go through it, that uh, it includes all syntax directed definition based on LL1 grammar. Okay, you can, if you want to remember, then it is fine. If you don't want to remember, then also it is fine. Okay. Now, a syntax directed definition is L attributed. When a definition can be called L attributed, if each inherited attribute, inherited, I hope you can remember, inherited means IPS terms. It was taken from parent or sibling, right? So when an attribute is taking the values from parent or from sibling, that is called inherited attribute. Attribute of xj of production, a like x1, x2 to yn depends on only on the attribute of the symbol x1, x2, xj minus 1 to the left of xj. What does it mean? It actually means, let I have a production that A is generating the value, A is generating the value x1, x2, x3, x4 and xn, right? Now I know, you know that as per the inherited attribute criteria, it will be checking the values from parent or from the sibling. Parent means from, this is the parent A, or from siblings. Let I have a target node of x3, right? I am calculating the value from x3. As per the inherited attribute criteria, the values will be coming from the siblings, right? Or may come from the parent, right? Now, under the L attributed, just we are modifying that inherited attribute definition, that yes, we will be taking the x3 value, or when we will be calculating the x3 node value, then we will not look to the right side siblings. So right side sibling means this one we will not take, this one we will not take. So we will be take the left side siblings of that particular node, this one. We will take the left side siblings of this one and also the root node, this one. This is the only definition. So that means this L attributed definition means for a particular node, when I will be evaluating the value, it will follow the inherited attribute protocol. At the same time, it will not in the category, in this category, that while taking the value from sibling, it will not take the value from the right siblings. It will take the value from the left siblings and as well as from the parent. This is the only change you have to remember here. Correct? And also you can check that I have given a Venn diagram over here, that this is an S attributed definition. If you want to make it a subset, then L attributed has a superset. Correct? This is a superset segment. These only two parameters you can remember: what is the Venn diagram architecture and what is L attributed definition, and it is fine. Okay. Just the whatever I have said already, I have mentioned that you can check in this example. I said that if I am taking the values from y dot s, then x dot s. So here, if I am taking the value for y from a, or from value of y from x, it is okay, because y is taking the value from a or from x, either from parent or from the left sibling. But if it is taking the value from z, which I have marked in this rectangular shape, it is not permitted. That's why the cross mark is given here in the third, right? So the right siblings value it cannot take, only the root node value. Root node want to mean the parent values, or left sibling values it can take. Okay. Now we will be moving to the next scheme, that is called translation scheme. Okay, let me erase this segment because these are no, for theoretical purpose, this L attributed definition you have to remember, but for practical sense, here no such questions actually come either in GATE or even in your exams from this L attributed definition. Just what is L attributed definition, how it operates, that you can remember, or even if they form some questions, you know now that it based on the inherited attribute in a customized way. Inherited attribute in a customized way is an L attributed definition. So accordingly, you can put the values there also. Okay. Now we are moving to the next example, number 43. Right. Now we are moving to the scheme of translation. Now, syntax directed definition, what we see under the syntax directed definition? Syntax directed definition. Actually, mainly we seen that if there is a production A to BC, here we write B multiplied with C or B divided with C. Some rules are written, correct? Here rules means semantical rules, here productions. This was the structure. Let here we have A generates B plus C. It means actually B divides C. So this is a semantic rules I am writing. A equal to B star C, A equal to B divide C. So that means in the syntax directed definition, once I write the production rule in the side by side, I will be writing the semantical rule. But in in translation scheme, what I will be writing, I will be embedding the translation rule within the production. For example, if I am writing A to BC, right? So here what I wanted to mean that B multiplied with C, right? So I should mention that thing, this multi here. Actually, here means I will be writing in a modified way that A is producing B. Here I will write multiply C. So I am explicitly specifying that what they are doing. I am not explicitly specifying actually what I wanted to mean. I am not explicitly specifying here what they have to do again. Rather, I am embedding the semantical rule within the production. That is the difference between syntax definition and translation. translation scheme. For example, you see the example number 43, that will be good to understand here, that okay, I hope here you can get the real understanding once I put an example over here. Uh, Let here the production is given E to tier. I'm writing the productions. This is the first production, and they are writing if R from R there is a production. It may be a plus or minus T and R1, or it may be an epsilon. Then they are giving T to num. So this is very simple production rule. R2 R1 means you can assume it is R also if you have any doubt over there. No problem with that. E2 tier, R2 plus tier, epsilon, and T2 num. This is the simple three production rules are given. But as per the translation scheme, if it is syntax data definition, then in the right side I have to mention the semantical rule. As it is a translation scheme, I need to embed the semantical rule inside the production. What they are writing, you check that I have written here in this portion that once plus t, that means print plus t. That means this plus minus whatever I am doing, here the print operation we will perform here. The plus minus whatever I am doing, this plus minus actually will come here once I implement it. Okay. For num, we are printing the num here, not here. So once the num came, we will put the name here. We may put the num here, but here t is generating a single value. So whether I am putting in the right or left, that does not make any sense. But if some values are there, let it is v a multiplied by num. Correct. They are telling or 11 v num and y. Three attributes are there, v num and y. They are telling that num will be putting into this way. That means the syntax will be v, y, and num. Once we will evaluate the value, not here. Again, I am repeating that what it does mean. Here we are the meaning of this black coloring, whatever I have written in this screen, that this plus minus is an operator, right? But once I will evaluate the tree, then this plus operator will come in between t and r. So this is a semantical rule. They are telling that v, num, and y, three different variables are there. But once I evaluate, the num will appear at the end. So that means the expression will be v, y, num. Here the expression will be t plus minus r. Here the expression. So that means actually basically this is a semantical rules I am showing. But not explicitly. We are embedding that semantical rules within the production. Okay. Now let's see an example that will be good to understand. Okay. Let me erase this portion over here. Okay. Now only thing I am marking that if plus minus is there, just as per the statement given over here, that if plus minus is there, it will appear in the middle, correct? So plus minus is there, then the plus minus will appear here in the middle, it will come. And if num is there, just you see here, num is there, so it will coming in the right side. So also I am marking it is the right side, though it is a single variable, so it does not make any sense. Already I said, so it will be coming in the right side. Now let us form a tree for 9 minus 5 plus 2. This is an expression given, correct? For this expression, I have to use the production rules and subsequently I have to form a tree. Okay. Now let's see how the tree is being formed. We take a different ink over here. Let here is the root node. Here I am producing e to tr. Just I am checking here whatever I have written and I am writing that one only. So r can generate minus tr, minus t and r, plus minus tr, rule number 2 actually, minus tr. Then from t I can generate from t to num is there. So from t I am putting the value is 9. For t, then the value I am putting as 5. From r, there is an epsilon production I can make, or plus tier, I have to put a plus symbol. So I need to expand R. So that should be plus, this is T, this is R. So this plus operator came. So T directly it is producing 9 minus 5 plus 2. And R can put generate epsilon. So there is no necessity to say epsilon. Right? Now I hope it is fine. Why it is fine? Because you just check that if I draw an platform and if I put the node value, so here it is 9, here it is minus. So in fixed operation I am performing 9 minus 5, then 2, that before 2 it is a plus. So 9 minus 5 plus 2 if I put the values over here in this way. Okay, so in fixed operation or in order expression, whatever you want to say, that you can tell. Epsilon does not have any significance. I can say it is 1. Right. Now, this is the tree that I have formed based on the production rules. Correct. Only I have applied the production rules. Not yet I have applied the semantical rules. Right. Now, what the semantical rules are they are telling? They are telling, just one by one you check. They are telling that if plus R, when R is expanded to plus TR or minus TR, then this plus should appear in between T and R. Okay, so let us check where the R is expanded to tier. So R is expanded to tier, right? Here you can check that R is expanded to tier. So this plus operator should come here. So I am moving this plus operator here. Within red color, I am marking it as a plus. Right? So this plus operator is no more an operator. So plus is coming here. In the same way that again TR expansion is here, minus TR in the second level. So this minus symbol, actually this minus is moving here. That's why this plus has moved here. Now this minus also is moving, and this will be coming in this region, minus. So this minus will be no longer here, right? Now plus minus I have moved. For T, you know that it will be appear in the right side. Right side means, okay, so here T is here, so right side means here I will be putting 9. For T here, right side means it is here, it will be putting 5. Here again the T, here I will be putting 2. Right? So now this value I have given for the tree. Right? Now you know that as per the production rules, first I form the tree. Then as per the semantical rules, I place the appropriate operators where they said. Now I have to evaluate the value of the tree. Now in order to evaluate the value of the tree, what you need to do is, let me check whether any more inks are available or not. Okay, black is available. You need to start from here, and you need to check where you can reach out. Here in this way you need to approach, then you need to approach in this way, and finally you can evaluate the tree. This is the way how you should evaluate. So how we can evaluate? So 9 minus 5 plus 2 was the expression. So once I'm moving from here to here, what is the value? So 9, I am getting this red color 9. So all the red color node I will be taking here. So this 9, it is coming first. Then once I will be moving, no minus symbol, because minus has moved to in this position. So from here I am obtaining 5. This 5 I am obtaining first. Then once I am moving from here, just I could not reach out here, just you check. Here one thing you need to take, that actually I could not reach out to that node because here the path was there, I had to reach out now. So I could not get because the road was blocked. So now after that, after 5, the minus operator was there. So this minus operator will be coming. So this minus operator I have to write. Once I will be moving out from here, then here it is a 2. This 2 we will be writing, and here this is a plus operator. So 9 minus, what is the expression? The expression is 9, 5 minus 2 plus. This is an expression. So here also can check that this is an expression. So what we did, we had an expression 9 minus 5 plus 2, and we converted the expression into 9, 5 minus 2 plus, which is a postfix operation that we have made. Correct now? And how we had made? we had made using the translation rules that are defined inside the production rules. So if I summarize what I had seen here, that first production rules will be given. Inside the production rules, the semantical rules will be embedded. When someone will be asking you to evaluate for a corresponding to a string, first you need to form a tree. Once you form a tree, then appropriately you need to put the semantical values in appropriate places. Then it will be okay. Let me check whether any more examples are there. No more examples are given. Let me give one more example over here. I hope that will be okay for you to understand. Just hello. Okay. Let me take one more example. No. Let I am writing this production rule. Let you can take an example number 2. Again, the same example, not same example, the homogeneous type of examples I am putting here over the translation scheme. Let E is producing E plus T, or even E can produce T. Let T can produce T star F. F can produce, okay, no, T can produce, one more production is there over T. Let T can produce F, or F can produce num, right? Also, I'm embedding the semantical rules here in the back-to-back side. Okay, here let I'm printing E plus T is there. Then once this plus operator, it will be printing plus here, correct? So it will print plus. What does it means? This plus operator here, though it comes in between this E and T, but it will be printing after E and T. So that means the expression is changing to ET plus. I should not write here, but for your understanding purpose, I have written in this way. So the expression is changing ET plus. For if E to T expression is there, I am not doing anything. So I am marking it a blank. For to T star F, I am writing print star. What does it means? It will be changing to TF star. For F, I am putting it a blank. For num, I am putting that print num dot value. Printing num dot value. Right? So these are the semantical rules I have written. So first semantical rules, I am changing the plus operator from this position to after T. For only second expression, it is producing nothing. For third expression, again I am putting the plus of a asterisk operator after F. For the fourth production, just I am putting only new operations mode. For the fifth production, just I am printing the value. Now let someone has asked us to generate a tree for 2 plus 3 asterisk 4, right? Using these production rules, and let us what changes we will see in the inter expansion. Okay. I hope I should minimize the screen so that I can accommodate the entire tree here. Now first I'm starting the expansion. So from E, it is E plus T. E plus T. My objective is 2 plus 3 asterisk 4. Then this T is being expanded to T star F, because I had this operator plus operator and asterisk operator. So just I have obtained plus and asterisk. My task is now simplified. Now from E I can generate T, and from T I can generate F. And from F I can put a value. So value is 2. Now this is a plus operator, already it was existing. I have let me erase it and write it once again. Okay, this is a plus operator. Now begin from this T to F, then F2 the value is 3, I'm writing for f, directly I can put a value number, so it is a 4, right? So that means the expression is 2 plus 3 star 4. So that means the expression that they ask, for that we have built a tree, right? Now we had to embed the semantical rules. Semantical rules, what they said, if the plus operator is there, it will be coming to, just you check, I wrote here et plus. So after the t it will come. So that means this plus operator will move from here and it will appear here, the plus operator. So I'm marking an edge over here for your better understanding purpose. This plus operator is coming. So I'm erasing this part. Okay. For star, again the star will come here, and also I am erasing. You should not erase here. For your understanding purpose, I am erasing, but you should not do that in your exam copy. So star is coming here. For f, directly I am taking the value for num. Okay. So that means for f, it is giving the value directly num. No changes are there, right? This is an expression that we have obtained. So now I am marking the all the nodes in red. This is 2, this is 3, the leaf nodes actually. 4, this is asterisk, and this is plus. And now you know we have to traverse the tree from in this way, I said. And now whatever the value we will obtain, we will take that one. So what will be the value if we take it? So it will be, I hope you can do it, 2, then it is 3, then it is a 4, then I'm moving to star, then plus. So that means I'm changing it to 2, 3, 4 asterisk plus. This is an expression I have evaluated by finding the semantical rules embedded within a production. I hope that you have understood it well. Uh, Let me give one more example so that we can be familiar with this structure. Okay. 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 Let the example number 3. Let here there is a production is given S2 XXW, or S can generate, for example, Y S, and W is producing SZ, right? Now what I am writing, that here I am embedding the production rules. Here it will print 1. Here it will print 2. Here it will print 3. What does it mean? If X, X and W is there, in the right side we will be printing 1 if entire expression is there. If this expression is there, in the right side you will be printing 2. I may have printed this print 1 in here. So that means if XXW, this expression is there, instead of that we will be putting 1 in the right side. But if we had written this print 1 in this position, then we will be printing 1 before XXW, right? So the expression changes depending on the placement of semantical rules in the productions, right? Now let someone has asked us to design a tree for XX, let another X, quad X, Y, Z, Z. This is the expression given, right? Now let me form a tree first, then I hope then you can understand the entire structure. Take another ink. Okay. So first I'm starting with the root node S. I'm starting with the root node S. From S the expansion is XXW. So here X, here X, here it is a W. W can be expanded to SZ. I'm expanding it to S and again to Z. Again, S can be expanded to XXW because I need quad X. So S, I am again expanding to X, X and W. Then that means already I have obtained X, 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 X. So quad X already I have obtained. I need to obtain Y, Z, Z. So that means the Z to be expanded. Okay, but no expansions are there possible for Z. That means only a expansion possible over W. So we should expand W here. Okay, so W again is expanded to S and Z, S and Z, which further again S is expanded to Y. Right now, I hope you can guess what I have obtained. X, 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 the infix operation I am performing, quad X, Y, Z, and then Z. That means what they have said that I have obtained here, right? Now, as per the rule, semantical rules that I have given here, so here you see that I said that if XXW is there, that means here we will be printing 1. If XXW, then means here we will be printing 1. If W to SZ, then we will be printing here 3. If W to SZ, here we will be printing 3. S to Y is there, here we will be printing 2. Right? This is the structure. Right? Now we have to traverse the tree from in this way. Right? Now what are the values I am getting? Already you know the red color values are the leaf node values. So first is 2, then 3, then 1, then 3, then 1. So that means corresponding to this expression, our expression is 2, 3, 1, 3, 1. I hope you have understood now. Right. Let me take the final example on translation scheme. I hope it will be good for you. Or these 3 examples are sufficient to generate the expression already I have given here. So you can, okay, one more questions I am giving you to all. You can make a practice of it. Just let me delete the segment. Here I am writing a code. You can make a practice of it. Already the translation scheme I have covered on 3 back-to-back examples I have shown, and we have covered the strict definition where the semantical rules were explicitly mentioned, but in translation scheme it was embedded inside the tree. Basically, exams what they ask you, they give the productions, and inside the productions the semantical rules are embedded. They will give you a string. They will ask you what will be the output expression for the string. That means the tree expression they are asking you. Okay, let I am writing a code. You can make a practice of it. Let n to L, this is in production. I am giving an expression. I am not mentioning whether it is a syntactic definition or translation. Definitely, I hope you can guess what it is. Now, if L is there, L1B, L1B, or in the sense you can take it as a LB. Okay. If you are a bit confused with that, you can take it in that way. LB, or L can generate even B, and B is generating 0, or B can generate even 1. Right? Now I am writing the rules. N dot deval equal to L dot deval. Here I am mentioning L dot deval equal to, actually this L dot deval equal to, that's why I mentioned is an L1. That will be good because L1 dot deval, this L and L1 both are same. To why I have given L1, because again initially I wrote L1, then I erased it to delete the confusion, to erase the confusion. And later again I am putting L1 because here in the rules, when I am writing the semantical rules here, to denote this L is different with this L, it means this value is different, that's why I am putting L1. Otherwise you may have putting the same values over here. multiplied by 2 plus b dot dval. For single b, it is L dot dval equal to b dot dval. For here, b dot dval equal to 0. Here it is b dot dval equal to 1. Correct. So these are the semantical rules I have written explicitly for all the productions, right? Now I am asking you, the string is given as 1011, right? So it's corresponding, it is in base 2. If I convert it into the decimal, then binary to decimal, it will be probably, it will be 11 base 10, right? So whatever the semantical rules I have written, first you draw a string for 1011, then you apply the semantical rules over the nodes, and you will find the value as in 11, correct? So that means what I wanted to tell here, that you should draw the tree, correct? You can do it. If you are not able to generate the expansion, just I am drawing the expansion here. From n you can make L, from here L you can generate L to B, then again from this L you can generate B, from again L, this is L and B, from this L this is finally B. So all the B's you can put either 1 0 or 1, so you can put 1, this is 0, here you can 1 and 1 finally. Now for this tree you need to evaluate the root node of the tree n, correct? You will find the value will be coming as 11. So what I wanted to tell here is that inside the semantical, in the compiler right now, you know that compiler, actually computer understands only the binary things, correct? Now so how the values, numerical values you are putting in binary, in the decimal mode, are changing to binary mode. Basically inside the compilers, when you are putting a suppose a value as in 11 you are putting, so these some sort of reverse semantical rules are embedded inside a computer, right? And once these semantical rules are embedded, they can change the values from decimal to binary or binary to decimal, correct? So that's why the semantical rules are very important in way to evaluate the tree. Again I am right, again I am telling the same thing. Syntax analysis was doing the, it was telling whether I have to move in top down or bottom up manner, and associated parsers it was attaching. But in semantic analysis, it is evaluating the tree. It is changing the abstract syntax tree to complete syntax tree where the value is being evaluated. Okay. This is all about your semantics analysis. In tomorrow, the 3 address code and some sort of code optimization I will be putting. I need some 2 to 3 classes more, and by that time we will wrap up the entire syllabus. And by this week, I will be uploading all the videos. You can wait. Thank you very much.